Okay. Exploring the properties of exponential functions. So, in order to do this, I want to compare them to some function you guys already know a few things about. So in grade 9, at the beginning of grade 10, you guys would have focused on linear functions. The standard linear function is y equals x. Okay? And in this case, if you guys recall from y equals mx plus b, our slope is 1 and our y-intercept is 0. So what that means is we have a line that's pretty much a 45-degree angle going like that. Okay? Some of the things we know about this type of function is that its rate of change is constant. Okay? And what that means is essentially the slope, the amount it goes up by, is always going to stay the same. Hence why we call it a linear function. It creates a straight line. So if we go over 1, we go up 1. That process stays the exact same.
Rise over run.
Yes, that's right. Your slope. Rise over run. It's the exact same thing. Okay? So in other words, it's a constant rate of change because it's linear. Another way you could figure something like this out is, let's say, I'll just do it quickly on the side. If we have a small table and we have our x and y coordinates, we find what's called, anyone remember the first differences? We did at the beginning of this year. We find the differences of those, and if the first differences are all the same, then we know we have a linear function. Okay? Quadratics. Here's a standard form of a quadratic function. We spent like 4 chapters talking about this stuff. Yeah, a parabola, that's good. And this is our standard or normal function for a parabola. We know that it starts at the origin 0. We go over 1, up 1. Over 2, up how many?
4.
Good, I'm glad you remember. Over 3? 9. Okay, so its rate of change is a little different. It's a little different compared to a linear function. Each time we go over, so I go over 1, up 1. Over 1, up 4. Okay, well in this case it actually goes up 3 from the one before it. Okay, so think of it like going over 1, up 3. This one goes over 1, up, goes up 5 from where it was before. So, with that same pattern, okay, what do we seem to be doing here? In terms of what are we changing by? Yeah, it's going up by 2. Yeah, we are making a staircase. And it seems to go up by 2 every time. So, if I were to go over 1 more, how many more would I end up going up? 7, that's right. That's the pattern of a parabola. Okay? We're just adding 2 in terms of where our original point was before. Now finally, this is a more complex version of a exponential function. We'll mostly look at exponential functions like this. The power is our variable, and they'll give us some number here. So in this case, I have the number 2. We're actually going to put this together as a group and then try to figure some stuff out with it. So, what I'm going to want to do is, I'm going to probably want to work around the origin. So I'm going to start at, let's say, -3, -2, -1, 0, 1, 2, and 3. Those are going to be the x values. We're going to plug it into this equation, y equals 2x. And we're going to figure out our y values. Okay? So in the very first one, when x is 3, y is equal to 2 to the power of -3. Without using a calculator, how can I make that a positive exponent? 1 over 2 cubed, or to the power of 3, which is equal to, that's right, 1 over 8. In other words, an eighth. So that's one of our coordinates. At -3 and an eighth. Very, very close to the x-axis. Let's try another one with -2. That's right. Instantly going to be 1 over 4. We flip it, and then we take it to the power of 2. If you're unsure how to do that, just try it with your calculator. Okay. So here's another coordinate. It's getting a little, it's rising up a little, -2 and a quarter. Still pretty close to the origin. -1. So this is going to be 1 over 2. Okay. So it'll be a half. Again, rising up. So we go up to a half. When x is 0, so y equals 2 to the power of 0. What's our y value? 1. Okay. So this is known as our y-intercept. Okay. And this is going to be really important because we're going to refer to the y-intercept a lot with exponents. Y-intercept is 1. In fact, unless we have values for a and c, the y-intercept for all exponential functions will always be 1, because no matter what number we put to the power of 0, it's always equal to 1. Okay, so our y-intercept will always be the same unless we have values here at a and c. Okay, now from there it starts to change a little. What is 2 to the power of 1?
2.
Right, so we're going to get 2, so this will be another coordinate. So we have a value at 1 and 2. What about 2 to the power of 2? It's going to be 4. So we're going to have a coordinate at 2 and 4. What about 2 to the power of 3? So we're going to have a coordinate at 3 and 8. So if you notice this function, starts off very small, starts to rise, and then it picks up speed or increases its slope greater and greater every single point. Okay? So we're actually just going to focus on to the right of the y-axis to start, and then we'll talk about what's happening to the left of the y-axis over here. If you notice, when I go from 0 to 1, I go over 1, I go up 1. I then go over 1. I go over 1. How many do I go up? From 2 to 4. That's right. Then I go over 1. How many do I go up? 4. Okay. Anyone know what pattern's happening here? We're multiplying by 2. Khalil's on the ball today, man. We're multiplying this pattern always by 2. So, from here I'd go over 1. How many would I go up? 8. Okay? That's the pattern of an exponential function. Now, I'm just going to refer back to a quadratic again. Remember, when we have our quadratic values in a table, we take first differences, they won't be the same. If we take second differences and they're the same, that means it's quadratic, right? Well, in this case, first and second differences will not help us at all. We actually have to divide our values, okay? So what we're going to be doing is you take one value and divide it by the other, and you should get a similar ratio every single time. If the ratio is the same, we'll have an exponential function. So I'm going to take those values, and I'll just focus from 0 up to 3, okay? So we'll go our x and y values. We have 0 and 1, 1 and 2, 2 and 4, and 3 and 8. Okay, I just took the bottom parts of this. We only need so much information to really assume the rest is the same. So what I'm going to do to figure out if it's exponential is I'm going to take, we'll call it a division. Okay, so first divisors, I'll call it. Okay, so instead of subtracting, we divide. And whether you divide the top from the bottom or the bottom from the top, as long as they're the same, that's fine. If we decide to divide the bottom from the top, it'll actually tell us how much our graph will increase by, or our rate of change. Okay? So if I take 2 and divide it by 1, what are we going to get? Good. All right? Then we'll take 4 and divide it by 2. What are we going to get? That's right. 2, and then 4, or 8 divided by 4? Perfect. Okay? So if you notice, our divisors are all the exact same. So we know this is an exponential function. That's how we would know by looking at a chart. It also is telling us our rate of change, what we have to multiply by. We know that we need to multiply by 2, our previous value of y, to always figure out where the next part of the pattern is going to be. Okay? So that's to the right of this. Now, I want to focus on the left of this. It's kind of hard to see. All that's going to happen is going to get closer and closer and closer. I know that's not a great representation to the x-axis, but it's actually never going to hit it. Okay? And now this is a new concept to you guys. This is called a horizontal asymptote. Okay, so I'm going to draw a line there. This is called an asymptote, but I'm going to make sure I spell it right here. A-S-Y-A-M, is it P-T-O-T-E? Yeah, P-T-O-T-E. This is a horizontal asymptote. And what it means is this function will never touch this line. So, to think of that realistically, guys, this is an important part here. Let's think of this realistically as if you're a human being. Okay, this is Griffin. Okay, he decides I want you guys to think of this theory. He decides to walk halfway to this wall. This is our wall. So he walks halfway. Okay? He then decides, once he stops, to walk halfway again. He then decides to walk halfway again, halfway again, halfway again. Will Griffin ever make it to the wall? No. He'll never make it to the wall because he continuously walks halfway to it. That's what an asymptote has a similar idea. We get closer and closer and closer to it, but we never reach that asymptote. Okay? Now, the equation of this asymptote is when y is equal to 0. Okay? So we have a horizontal line right across the x-axis for exponential functions. They'll never touch the x-axis, so there's no x-intercept in these types of questions. Okay? I think that covers most of it. This value here, okay, I'm going to focus on the b again. This is when b was greater than 1, right? That was our value of 2. We have an exponential increase. If our b value is less than 1 but greater than 0, so in other words, something like y is equal to a half to the power of x, instead of growing, think of decay. It's going to come downward. So our function will look something like this. Okay? And it will also still have a horizontal asymptote at the x-axis, but it's a little different. The y-intercept is identical. It still goes through the value of 1. Okay? But it's going to be coming down from the left side towards the asymptote on the right. Okay? So that's when our value of b is less than 1 but greater than 0. So in other words, between 0 and 1. When we're greater than 1, we grow. And when we're less than 1, it shrinks. Okay?